Okay, welcome to the fourth video in this series, and in this video we're going to talk about the composition of systems. So what do we mean by composition? Well, basically in the real world we have lots of different systems which are interconnected with each other and maybe pass signals to one another. One thing that's very helpful that we can do is that we can actually treat each of these smaller subsystems together as some larger system, and this is very helpful. So for example, we could consider concurrency. So we could consider that systems SA and SB are synchronized together by some interconnection relation, which we'll use this kind of fancy I to describe. So then, we can use this term here. So we have system A with the composition with the interconnection relation I with system B. So let's define this. So let's imagine we have two systems. We have SA, which has a set of states, initial states, inputs, transition relation, outputs, and the mapping from state to output. And we have system B, which has the same things. We can define this interconnection relation I, which is a subset of the composition of the states of system A with the states of system B, with the inputs of system A and the inputs of system B. And so this can describe how system A interacts with system B. So we denote this, as already mentioned, using system A, the composition with the interconnection relation, and system B. And we can write this now as a new system which has a set of states x, AB, a set of initial states x, AB, 0, a set of inputs u, AB, a transition relation of AB, outputs y, AB, and a mapping h, AB. So this set of states x of AB we can describe by using a projection map, so pi with a subscript x of this interconnection relation. And so this projection map says that we can take the set of elements in the interconnection relation here, and we can map it to some smaller set of elements and some smaller set representing just the set of states of XA and the set of states of XB. So this means that X of AB is therefore some description of the composition of all these states together. We can also describe the initial states, XAB0. So this is going to be the set of states XAB that we have here, intersected with the composition of the initial states of system A and the initial states of system B. So if these two systems have the initial states mapping to their state spaces, then it's possible that this state space again would be, the set of initial states would be the full state space. But if this is some subset of the states of each system, then we'll have some smaller relation because of the intersection between these two sets. We can also define the inputs of this composed system, which will be the inputs of system A composed with the inputs of system B. And we can define the transition relation, where we can have an element of system A and an element of system B, which have some transition relation with inputs, input A for system A and input B for system B, going to some new states, XA dash and XB dash. And these will hold if these three conditions hold. So the three conditions we have, the first two are very straightforward. So the transition XA with input UA to XA dash should hold for system A. So this makes sense. It should, if we're going to do a transition, it should be possible that the transition actually exists within our original system SA. Otherwise, we're composing something that never existed to start with. And our second condition is just the same thing for system B. So some state XB with some input UB transitioning to X dash of B should exist within system B. And then finally, the third condition we have is that the elements that we have here, XA, XB, and then the inputs UA and UB, should exist within this interconnection relation which we described. Finally, we have our outputs, which can be described as the outputs of system A composed with the outputs of system B, and the mapping of HAB for these two states is just equivalent to the mapping of system A for state A and the mapping of system B for state B. So one thing that's great about defining it this way is that then we can learn some things about the behavior of the system and about the type of composition we have going on. So if we look at this composition of system A with system B with the interconnection relation I, then we know that actually this behavior of this interconnected system is some subset or potentially equal to the behaviors of system A and the composition with the behaviors of system B. And so the closer this behavior of this interconnected system is to the full composition of the behavior of system A with system B, then the more trivial the interconnection is between these two systems. So let me try and explain this a bit clearer. So if we have two systems which have separate behaviors, if they're only weakly coupled to one another, then in many ways there'll be almost no restrictions on either system based on how they operate. So you could have one system is operating over here, one system's operating over here, and there's very little crossover, so both behaviors can be completely occurring on their own. And so then this interconnected behavior is therefore going to cover almost all of the behavior of both of those systems. However, if they're strongly coupled together, then the behavior of system A or the behavior of system B, the strong coupling means that they're interacting with each other more, which might prevent the system from doing certain things. So let's imagine we've got a temperature sensor and you've got two systems describing this, and maybe they're both controlled, and one system is trying to increase the temperature of the room and the other system's trying to decrease the temperature of the room. Well, the behavior of this interconnected system is going to be a lot more limited because it's got to somehow balance out this conflict between these two system descriptions that are working against each other. And so this behavior is going to be a much smaller subset of the behavior of the two original systems. But if we were to describe the systems as rooms which are next to each other, then it might be possible that actually there's very little interconnection between those two rooms. Maybe there's a very high resistance between in the walls, so it means that there's very little temperature exchange going on between these. In that case, then the behavior of this system might well be almost all of the behavior of the first room and almost all of the behavior of the second room. So finally, let's look here at just a few different ways that this interconnection relation could be described. So I've drawn four systems here and how they connect. So in this first case, we've got the system SA and the system SB, and we're saying that the output of system SA is being used as an input for system SB. So therefore, the mapping of the state XA would then be equal to the input of system B. In this second case, we could say that that's happening for both systems. So both system outputs are being used as an input for the other system, and so these two would be much more closely coupled together because of the interaction between the systems. In this third case, we could say that when we select an input, the input we're selecting is being applied to both of the systems. So this will have interesting impacts on the behavior. So if the systems behave in a very similar way, then that input will make both systems behave similarly. But if these two systems have very opposite behavior, then the same input might make one system go one way and then the other system go the other way, for example. And then finally, this fourth system we've got here, we're just saying that the outputs of the two systems are the same. So we could have different inputs being applied to the two systems, but then we're trying to enforce in some way that these two systems actually then have the same output. And so to get this behavior, this might be a lot more restrictive of what can be done within the system to get this behavior to happen. So this was just a very general description of composition, and we're going to look a lot more in detail on this in future videos. All right, bye for now.